Hi, in this video, I'm going to be talking about active learning a convex body in low dimensions. I'm a PhD student at the University of Illinois, and this is work with my advisor, Sariel Harpled, and a collaborator, Saladi Rahul, at the Indian Institute of Science. So let's just dive right into the problem that we're going to be talking about today. You're given a set of points in low dimensional space. Let's just think about the plane for the time being. And you also are given a convex body C. The question is, how are we given access to the convex body? Well, you're given access to it via some sort of oracle query. So in this case, we consider the oracle query to be a separation oracle. So what this means is that given a query point, the oracle will either tell you that the query point is inside the convex body, or it will tell you that the query point is outside the convex body, and also give you a separating line as proof that the query point does not lie inside the convex body. The goal is we want to compute the collection of points inside the convex body, and likewise the collection of points outside the convex body, using the fewest number of oracle queries. You can see in this figure below an example of a separation oracle. And here is just the problem that we want to solve. So again, we're given a set of points in the plane. We have some unknown convex body, and we only have access to that convex body via this oracle. And we would like to classify all of the points as either being inside or outside this convex body using the fewest number of queries. So the motivation for this problem comes from active learning. So in the active learning setup, you have an input space, and you want to build a classifier over this input space according to some concept. And so you're given learner data and items x1 to xn, but they are not labeled according to this concept class. And the learner is allowed to query the oracle or a teacher for the label of any point in the input space. So it doesn't just have to query the labels for x1 to xn, but it can query the label for any point in the input space. And so using this, you would like to make as few queries as possible so that you can build a classifier over the learner data, and hopefully this classifier extends to the full input space. So the question is, what queries should we pick? And how many queries do we need? Some additional motivation for this problem is recall that we will be dealing with separation oracles, and in general, separation oracles are well known. They're used in operations research, in linear programming, and so on. And from a computational geometry point of view, there have been other problems within the computational geometry community that have been studied where you are trying to solve a problem with access to some specific oracle. So for example, things like nearest neighbor oracles, proximity probes, linear queries is a recent one where given a hyperplane and a point, you assume that you can efficiently test which side a point lies on of a given hyperplane, and so on. So we consider this just to be a natural problem on its own, with obviously motivations from active learning. So I'm going to talk about one approach that you first might think of when you're going to try and solve this problem. And let's just simplify the problem a little bit and allow ourselves to have some error in classification. So what I mean by that is you have to classify all points as either inside or outside, but you're allowed to make an error on, say, at most epsilon n of the points. And when you're allowed to make error, there's this approach called pack learning. And the algorithm is very simple. You take a random sample of your input or of your learner data. You obtain labels for that sample. So you ask the teacher or the oracle for the labels of every item in your random sample. And you just build a classifier over this random sample. And the hope is that this classifier for the random sample is good enough as a classifier for your learner data and therefore for the original input space. So pack learning then studies the problem of simply the sample size, right? If you take obviously a very large sample, you would expect that the classifier is going to be much better as opposed to when you took a small sample. So it turns out that if you look at, for example, learning a half space, right? So what the algorithm does is it takes a collection of points, it builds a half space classifier, right? And the points that it misclassifies is going to be the symmetric difference of the learned and true classifier. So you see here in the picture below, I have my learned classify, which is this red half space, and you have the true classify, which is this green half space, and the error that I make is going to be the set of points lying in the symmetric difference. So it's in these two yellow wedges here that I'm highlighting. So for half planes, the symmetric difference is a wedge. And it turns out that using some machine learning theory, wedges have finite VC dimension. And so it turns out that you can take a random sample of size, roughly 1 over epsilon log 1 over epsilon, and this will guarantee you that the classifier errors on at most epsilon endpoints. But remember, the original problem we were interested in was for arbitrary convex bodies. So in this case, the symmetric difference between the true convex body and our learned convex body could look like a ring here, which I've drawn. Again, in which the red outline is the learned convex body and the green is the true convex body. But it turns out that this scheme fails, and it fails primarily because convex bodies have infinite VC dimension. So this tactic alone doesn't work. Now, of course, in practice, people get around this by ensuring large margins around the convex body, and there are some other tools. But this is, from theoretical point of view, without any sort of additional heuristics, this scheme immediately fails as for arbitrary convex bodies. And really, the point of this slide is just to say that this sort of random sampling alone will not work. And even if you'd like to get an epsilon n error, you really have to do some sort of additional technique than just random sampling. But back to our original problem, in which we're focusing on just classifying points exactly. Now, you may have realized before that the worst case for the problem is that you may have to query all points. So it could be the case here on this figure I have on the left. I have a convex body, which is a disk, and all of my points lie very close to the boundary. Now, if this is the case, then why do you have to query all of the points? Well, let's say you query only n-1 of these points. It turns out that whatever answer you give for the nth point, I could adversarially change my answer and still be consistent with all of the previous queries I made to determine the membership of your n-1 points. So in some sense, this is bad news for us, but then you should think about the other scenario in which there are easy instances to solve, where if you have points very far from the boundary, right? So they're contained very much inside the convex body or very far away from the boundary of the convex body outside, then it's conceivable that there is an algorithm that could classify the points with a constant number of queries. So the goal here is to design instance sensitive algorithms. So what we mean by that is algorithms which perform well if the input is structured in a nice way. But if the input is some sort of worst case scenario, like the figure on the left, then we expect the algorithm to deteriorate to the brute force solution in which you just query every input point. Now, before talking about some of the results we have in this paper, I want to talk about the first thing, which is a lower bound we have on this problem. So what I'm going to present is a lower bound on the number of queries that any algorithm has to make in order to classify all input points correctly. So the lower bound is as follows. We define the inner fence, which is a polygon Fn, as the convex polygon with the fewest number of vertices, such that Fn is contained inside the convex body, and the set of points inside the convex body is the same as the set of points inside Fn. So in the three figures above, this is this dark blue polygon that I'm highlighting. And you can think of the inner fence as separating the points inside the body from the boundary of the convex body. Similarly, you can define the outer fence, F out, as the convex polygon with the fewest number of vertices, which contains the convex body, and the set of points outside the convex body is the same as the set of points outside the outer fence. And again, in these three pictures, that is the red polygon. Okay, so once again, this is the polygon that separates the boundary of the convex body from the points outside the convex body. And we can show that if you define the separation price as the sum of the sizes of each of these two polygons, then any algorithm has to make at least sigma PC oracle queries, where sigma PC is the separation price. So this matches our intuition in the worst case scenario that I mentioned, where if all of the points are very close to the boundary, the separation price is going to have near linear size, and indeed this lemma states that any algorithm has to make at least a linear number of oracle queries. So with that, I'm going to dive into the results that we have. So the first problem we studied is this classification problem in 2D, where again, the lower bound on the problem is the separation price sigma PC. And the algorithm that we had first is a greedy algorithm, which uses k log n queries, where k or kp is the largest number of points of p in convex position. So a set of points are in convex position if you take the convex hull of the points, and every point is a vertex of the convex hull, or equivalently, a set of points are in convex position if no point is a convex combination of the other. We were able to, in fact, improve upon this algorithm, so we get a second algorithm for the classification problem, where the number of oracle queries we make is sigma PC times log squared n. Okay, so this matches the lower bound up to a factor of polylog n. And these were both of the results we had in 2 dimensions. We then went on to study the problem in 3 dimensions. So in 3D, the separation oracle doesn't return a separating line, but it returns a separating plane. And there we were able to extend the first algorithm into 3D to also get an algorithm where the number of oracle queries is k log n. I haven't mentioned a lower bound here, just because I haven't defined the lower bound in 3 dimensions. You can extend the notion of separation price to high dimensions, and that's provided in the paper. But I mentioned that this is the best result we have for 3D so far. We don't have any better algorithm in 3 dimensions. We also studied the verification problems, where you would like to verify that every point is inside the convex body or find a witness point outside the convex body. So there, it's not hard to see that a lower bound on the number of queries you need to make is the size of the inner fence. And we get an algorithm where the number of queries is at most the size of the inner fence, log n. Similarly, you can consider the verification task where all of the points are outside, or you'd like to find a witness point inside your body. And again, we get an algorithm which is polylog n away from the lower bound. The rest of the talk, I'm going to focus on the details behind the first algorithm, which is a greedy algorithm, since that's the simplest for this talk. So just some remarks about this greedy algorithm. So again, it runs in k log n, or rather it uses k log n queries, where k is the largest number of points in convex position. So it was previously known for this problem that you could solve it using k log n queries. And this actually follows by a framework of Kane et al. In 2017, using something they call the inference dimension. So it turns out for our problem, people familiar with inference dimension is that the inference dimension is simply k. And so their framework immediately implies this k log n algorithm. But their algorithm is randomized. So algorithm is deterministic. And of course, we improve the number of queries by a log k factor. You can also implement the algorithm very efficiently. So the implementation time is roughly n polylog n plus t k log n time, where t is the query time, or the time needed to perform an oracle query. So really what this says is that the bottleneck for the algorithm really is the time needed to perform a separation oracle query. It's also known that if you choose a set of points uniformly random from the unit square, in other words, here k is a random variable, then the expected number of points in convex position is theta of n to the 1/3. So this implies immediately that for any convex body, if points are chosen uniformly random from the unit square, the number of queries you need to make an expectation is sublinear in n, roughly n to the 1/3 log n. So how does this greedy algorithm work? The first thing it's going to do is it's going to maintain an approximation of the convex body. So I call this the inner approximation, and it's called B. And you can think of the inner approximation as the convex hull of all of the queries which fall inside the convex body. There are 2 main operations that the greedy algorithm will use. The first operation is expand, which, given the inner approximation B and a point P, will simply update B to be the convex hull of B and P. Okay, so in this figure below, I have B and I'm adding P to the inner approximation. And in the process, I may get to classify additional points. The other operation is remove, in which given a half space L, I can simply classify all of the points as inside the half space as outside C. Okay, so here I'm having the precondition that the half space L does not contain the convex body. Finally, we also need center points. So recall that point C is a center point for P. If for every half space L, if C is an L, then this implies that L contains at least a third of the points of P. It turns out that center points always exist, and they can be computed efficiently in n log n time for a collection of n points. So here's how the algorithm works. We have a set of unclassified points U at any iteration during the algorithm. So while U is not the empty set, we choose the half space, which is tangent to the inner approximation, which has the most amount of points inside it. Okay, so in this figure below, I have unclassified points, which are gray. I have my yellow convex body, and I have my blue inner approximation B. And the green points are points that we've already marked as being inside the convex body. So we choose a half space L, which contains the maximum number of points and is tangent to my inner approximation. Next, we compute the center point of the points lying in this half space. So in this figure below, it might be this red point here. And we query the oracle using this center point. So there are two scenarios. If the center point happens to be inside the convex body, then we can improve the inner approximation. So we expand the inner approximation to include this point C. If the center point C is outside the convex body, then we get a separating line H. And what we can do is we can classify all points lying above H as outside C. Okay, since if C is outside the convex body, then all of the points on the same side of the half space as the center point is also outside the convex body. So in the scenario below, because the center point's inside, we would expand the inner approximation like so. And in addition, we classify 2 extra points in this case. Okay, so now what I'm going to do is move on to an animation of the algorithm. Okay, so here's an animation of the algorithm. We have a set of points, which are these white points, chosen uniformly at random from the unit square. And the yellow polygon is our convex body. You can see the algorithm working where the blue polygon is the inner approximation. And these purple points are the oracle queries it makes in each iteration. So in each iteration, you can either improve the inner approximation, or if the query falls outside the polygon, then we can classify many points as inside. So if we let this just play out for a few more iterations, you can just get a feel for how the algorithm works. Here, I'm also considering the worst case scenario in which the algorithm always returns the separating line that passes right through the query point if the query point falls outside the convex body. And this doesn't affect the performance of the greedy algorithm. And the algorithm will just keep proceeding in this fashion until all of the points have been classified. So let me swap back to the slides now, and we'll talk about how you analyze this greedy algorithm. Okay, so how does the analysis of the algorithm work? The idea is to count visible pairs of points. So what I mean by this is at any point in time, we have our inner approximation B, and we have a set of points lying outside the inner approximation. And what we say is that 2 points are mutually visible if the segment connecting them does not intersect B. Okay, so you can see in this figure on the right here, I have my inner approximation B, and I've drawn all green edges between all pairs of points, which are mutually visible from one another. And this turns out to be the right potential function to analyze for the algorithm, where in each iteration of the algorithm, we either argue that many pairs lose visibility from one another, and this happens when we improve the inner approximation, because as we expand the inner approximation, the expansion is going to kind of cut the edges in this graph and points lose visibility. We can also argue that if the query falls outside the convex body, then many points become classified, right? Because we obtain a separating line. And so we can just delete many points from this graph. So essentially the idea is we just count the number of pairs that lose visibility in each iteration in each of these two scenarios. And so because we're choosing center points as our Oracle queries, you can argue that in some sense, a constant fraction of points or a constant fraction of pairs of points lose visibility. So this implies that the algorithm makes k log n queries, where k is the largest number of points in convex position. Let's talk about extending the algorithm to 3 dimensions. How does that work? So here I've pulled up the pseudocode that was for the greedy algorithm in 2 dimensions. And the only thing that changes from 2D to 3D is that now we get a separating plane. Okay, that's the only difference. But the analysis is much more difficult. Why is the analysis more difficult in 3D? So B is an inner approximation now, which is a polytope in 3 dimensions. And the problem is that before, our potential function was to count the number of pairs of points which have visibility between each other. But in 3 dimensions, when you improve an inner approximation, pairs of points do not necessarily lose visibility. You can think of 3 points forming a triangle in 3D, and the inner approximation can kind of expand through this triangle, but each pair of points in the triangle have not lost visibility from one another. But this kind of gives us a hint that we should then look at triples of points. So we need to have a potential function which analyzes the number of triples of points that are mutually visible from one another in each iteration of the algorithm. So then we maintain 2 graphs in the analysis. We have the first graph, which contains the set of points, and 2 points are connected by an edge if their segment avoids the inner approximation B. And then we also have a hypergraph, where again, the vertices correspond to points, and 3 points form a hyperedge if the triangle PQR avoids B. And similarly, you can go through the analysis again, and the greedy algorithm in 3D turns out to also use k log n queries, where k is the number of points in convex position. So I'm just going to finish with some conclusions here. So I've brought up the results that I mentioned earlier. Of course, the first big open problem that we can talk about is shaving logarithmic factors. So all of these results are more or less a log factor away from the optimal solution, and so improving the log factors is a natural problem to state. The other thing is that the optimal algorithm for 2 dimensions, or rather the algorithm that is a polylog factor away from the lower bound, is not very natural. It took us a long time to get to that algorithm, and the analysis is also not very easy. And so it'd be nice to get a more straightforward algorithm in 2 dimensions that matches the lower bound up to some polylog n factors. The other question is, can we get something which is near optimal in 3D in terms of the number of queries? I mentioned that we do have a lower bound on the number of queries in 3D, and this follows by extending the separation price to higher dimensions, but this k log n algorithm is the best thing that we have so far. The question also is higher dimensions. Of course, with the motivation coming from active learning, it would be natural to try and study this problem in higher dimensions, but we think even the 2 and 3 dimensional problem was quite hard. So going up to high dimensions definitely would be a challenging problem. And that's all I have to talk about today. Thank you for listening.